Hey guys, welcome to our second lesson of week 3, where last lesson we looked at binomial products, and we're going to continue that today, but with a very specific goal of expanding perfect squares and difference of perfect squares. So we're going to learn what those are today. Starting, of course, with a warm-up, I'd like you to expand, which remember means expand and simplify, these two binomial products. So take a moment now to complete those before we move on. So what is a perfect square? A perfect square is just a square number. So for example, 3 squared, which is 9, is a perfect square. A squared is a perfect square. 2y all squared, you see where I'm going with. If you have a binomial expression all squared, that's a perfect square as well. And here's another binomial expression all squared. So basically anything where the entire term or culmination of terms has a squared after it is what we consider a perfect square. So when we look at binomial expressions, which is what we were looking at last term, squared, such as a plus b squared or a minus b squared, this is what we call expanding perfect squares with binomial products. So if I have a plus b squared, that's the same as a plus b times a plus b. Now it's really important that you remember this expansion step. I'm then going to use the distributive law, all right, to do my first, outer, inner, last expansion to end up with a squared plus ab plus ba plus b squared. Now, after we've done that, this term here, AB, and this term here, BA, are in fact like terms. So we can bring them together and we actually end up with, A squared plus 2AB plus B squared. So what this means, guys, is that every time we have A plus B all squared, we are going to have the answer a squared plus 2ab plus b squared. And that's a general rule for expanding perfect squares. Now we're going to have a look at the second situation of expanding perfect squares. And don't worry, we're going to put numbers in for a and b soon. Okay, and I'm going to show you how to use this as sort of a shortcut to a full-on distributive law expansion. So let's have a look at a minus b all squared. That's a minus b times a minus b. Then we use our distributive law, first, outer, inner, last, to expand this. So we end up with a squared are the first terms minus ab minus ba plus b squared. Okay, so look at that now. We have minus b times minus b is positive b squared. These guys here are like terms, so we can bring them together and we end up with a squared minus 2ab plus b squared. So another little general rule is that if you have a minus b all squared, you end up with a squared minus 2ab plus b squared. And that's our second little shortcut rule that we might be able to use later on. You notice the only difference between these two things is that a plus b all squared ends up with all pluses once you use your distributive law. A minus b all squared ends up with a single minus there. Okay, so that plus b squared term is positive at the end. I know this doesn't make a lot of sense yet. We are going to do some examples shortly. So these are perfect squares. A difference of perfect squares is where you have a plus b and then a minus b. So rather than it being a plus b all squared or a minus b all squared, we have the same first term in both brackets. We have the same second term in each bracket, but the difference is that there's a plus here and a minus here. Let's see how that checks out once we expand it. First of all, we'll end up with a squared. We'll do our outer terms, inner terms, and last terms. So a squared, All right, the outer terms minus AB, the inner terms plus BA minus B squared. Okay, now check this out. These guys are like terms again, but they actually cancel each other out. If I have AB, negative AB plus AB, well, that's just 0, isn't it? So that actually simplifies right down to this. So as another and our third general rule of the day, a difference of two squares, if you ever see A plus B, A minus B, you can immediately, without going through any of the distributive law expansion, immediately write the answer as A squared minus B squared. All right, there's no C in this one. It's not Pythagoras. How sad's that? Okay, so let's get stuck into some examples. So our examples down here, I've got a perfect square, difference of two squares examples. All right, so let's do them together. Remember, what I'm going to do for each one is I'm going to expand this with the distributive law, but with this one here, I'm just going to use the rule that we learnt up here. Now, when it comes to your exam, you're welcome to jump straight into using these rules highlighted in green for your answer. But if you're not comfortable with them, just do what we did last lesson with the FOIL method, and that's absolutely fine. So I'm going to do it both ways. So with this one here, I'm going to expand it completely. All right, just because I can, not because I have to. All right, let's do my first terms. X squared, outer terms minus 2x, inner terms minus 2x. Final terms or last terms plus 4. Pop it all together. I notice these guys are like terms. I end up with x squared minus 4x plus 4. And that's my answer. For B, I'm going to employ this rule here. Okay, so I'm just going to immediately say if this term is equivalent to A and this term is equivalent to B, I'm going to state, well, my answer should be, and remember this is just me using the shortcut to show you how to use it, it's going to be A squared plus 2 times 2x times 3 plus 3 squared. So in this case, this is my A term and this is my B term. And look, it expands to A squared, so 2x all squared, plus 2AB, 2 times 2x plus 3, 2x times 3, sorry, plus B squared, plus 3 squared. And in my final step, I'm going to simplify all of that. So I end up with 4x squared. Remember, our index laws tell us that squared applies to the 2 and the x. Plus, now 2 times 2 times 3 is 12 plus 9, and that's my answer. So we notice that we only have one line less of working when we're doing the shortcut method for a perfect square. All right, so it's not that much quicker with a perfect square, but it is going to be a bit different when we get to the difference of two squares. So I'm going to do C in the same way I did A with my full-on expansion, and I'm going to do D with my shortcut. Let's get to it. So, first terms, x squared, outer terms, negative 2x, inner terms, 2x, last terms, minus 4. Check it out. Away they go. Minus 2x plus 2x is just 0. So my answer is x squared minus 4. Done. Let's now employ this rule here for this final example. And the reason I've chosen this example to employ this rule is we can see these are going to be kind of ugly. I've got 3x and a negative 2y, so I'm going to have to use my brain a bit if I keep expanding. But instead, I can just say, all right, well, I know that's going to be a squared. So we need to identify 3x as a in this case. All right, 3x squared minus b squared, which is 2y squared. Using our index laws, remember that squared applies to the 3 and the x, and that squared applies to the 2 and the y. My answer is just 9x squared minus 4y squared. And that's it. Remember, if you're not comfortable jumping straight to this step, please feel free to expand like we did in C as well. So guys, this looks like it's a lot of work, but it's actually not. With exercise 8B, I want you to have a go at a little bit of every type of question. So here we see perfect squares, some with coefficients, some without. Difference of two squares where x doesn't have a coefficient and it does. So I've just asked you to do, question 2C, question 3FI, question 4C, and so on, just to get a range of different exposures to those questions. Question 8 and 11 are your worded problems, and if you're looking for a challenge, have a crack at question 12N. You can email me